دكتور لاي، السلام عليكم.
السلام عليكم.
سلام، كيف الأمور عندك؟ تمام؟
الحمد لله. Just give me a second to set things up.
طيب ممتاز. ترى احنا وي ار لايف اون يوتيوب يا شباب. اوكي
إن شاء الله.
اوكي.
هلا أبو عمر، كيف الحال؟
الحمد لله بخير.
جاهز إن شاء الله؟
إن شاء الله.
انت كده توتر زيادة يا دكتور.
ليش؟ صوتي يخوف يعني؟
له اسبوعين يتدرب قاعد، عرفت؟
هذيك الاشياء بيننا يعني بلاش
عشان نلطف الجو. دكتور لاي، انا هحطك الان هوست. ها
اوكي.
بس انا ما يعني I'm not going to leave لانه الريكوردينج من عندي. ف
لازم يا أبو محمد، يعني ما نستغني عنك، تعرف.
الله يسلم. والله انا لانه عندي اجتماع 8 وعندي بعدين اجتماع الساعه 9، عرفت؟
الله يكون في عونك.
فبعد ما يخلص انا هاجي اقفل، فانت لا تقفل ولا شيء. تمام؟
اوكي.
في النهايه just يعني leave the room، وانا اللي هقفلها. فخليني احطك هوست. هلا منور، ما شاء الله. كيف حالك؟
الله يحييك.
ايش اخبارك؟
الحمد لله بخير.
طيب ما انتم مكاتبكم جنب بعض، ليش ما رحتوا في غرفه واحده وخلاص وكاميرا واحده
distance
social distance. ايوه social
ملتزمين يا محمد.
الله يسلمك، يعطيكم العافيه. طيب الامر راجع لكم، اذا تبون ننتظر يعني 8 و5 نبدا 8 و3، الامر راجع لكم لانه الصلاه دوبها خلصت.
هذا ممكن شويه.
طيب
احنا لسه يعني ما جت الساعه 8 صح؟
باقي 3 دقائق بس لاني متحمس. ايش اخبار السي اكس؟ خلاص خلي الناس تسمع الاخبار. السي اكس في اخبار جديده، الطلاب قاعدين يسالوا.
سي اكس الاي او تي.
الاي او تي
خلاص ان شاء الله، يعني في طريقه الى الابروفل ان شاء الله. يعني
هنبدا ان شاء الله الترم الجاي، السنه
باذن
الجايه.
الله. يعني هي it's just a matter of paperwork now. يعني all the work we have finished preparing the courses. We have يعني the proposal has already been sent. It's just in the pipeline.
بس عمليه الادميشن انتو ذا سي اكس متى هتبدا؟ الطلاب متى they declare
والله يعني أنا I did ask, بس I have no idea yet. Last year what happened in I think in at the end of the semester, the CX office contacted the students and asked them to send their choices. They went through them and they had to match students with their prerequisites for each CX. They see who qualifies for each CX and give the students the first choice if possible, يعني. If not, the second and so on. So I think they will go through the same exercise this year as well.
يعني نهاية الترم يعني.
I think so.
يعني مختلف. السنة الماضية كانت في الصيف مش في الفصل، يعني ممكن حتى يتأخر إلى الصيف شوية.
Last CX was during the semester. The MX كان في الصيف، بس the CX it was before. يعني before the students finish the year, they know what they are going to take next year. لأن مش كلهم موجودين في الصيف حسب يعني ما أعرف.
طيب الآن الساعة 8، فتبونا ننتظر كمان شوية دقيقة ولا تبوا تبدأوا؟
Well,
الأمر راجع لكم.
let's give it a couple of minutes, just 2 minutes more. عندنا يعني ما شاء الله في 21.
طيب أنا لأنه الطلاب الآن عندي اجتماع، الطلاب بينادوني، فخلاص أترككم في رعاية الله. طيب
التسجيل قائم صح؟
أيوة التسجيل على اليوتيوب على طول موجود. فيكون هذا أنت في الأخير بس إنه يعني لا تقفل الغرفة، أنا هاجي أقفلها.
أوكي
خلاص
خير إن شاء الله.
تمام. أنا هكون موجود يعني أونلاين، هتابع من عن بعد.
No problem.
الله بالتوفيق يا أبو عمر.
طيب توفيق الجميع.
السلام عليكم.
السلام عليكم.
نبدأ دكتور؟
والله زي ما تشوف، نبدأ.
ما دام يعني الإخوان موجودين. I think let's start. بسم الله الرحمن الرحيم. So I would like to welcome you all to this other seminar from the Computer Engineering Department. Our speaker for this night is Dr. Abdulaziz Al-Tabbakh. طبعا Dr. Abdulaziz is an assistant professor in the Computer Engineering Department. Dr. Abdulaziz has also graduated and got his undergraduate bachelor degree and master degree from the Computer Engineering Department and at KFUPM. And Dr. Abdulaziz has received his PhD from the University of Southern California, USC in Los Angeles. Dr. Abdulaziz is specialized in computer architecture and high performance computing. And more specifically, his research is in memory systems for GPUs and architecture for computing accelerators. And Dr. Abdulaziz is currently leading the effort in designing an MX program. MX is a professional master program that's a one-year program in high performance computing. And of course, this is a very important field for the current market, as all of you know now that artificial intelligence and other similar disciplines, they all rely on high performance computing to achieve their goals. So HPC is expected to be a very big market in the coming years, inshallah. And as many of you have already also know that KFUPM has the pleasure of now hosting at the DTV Dammam, is it called Dammam Arba'a, or I forgot the exact name, high performance computing infrastructure that's hopefully will be a game changer in the coming years. So today, Dr. Abdulaziz is not going to talk about high performance computers, but I will talk about embedded systems, which also play a main role in many applications, including IoT systems, and a lot of the systems we deal with daily. So I would like to open the floor for Dr. Abdulaziz to start his talk. And please, if you have questions, you can keep them, ask them at the end, or you can also throw them in the chat. I will be, inshallah, moderating the discussion at the end. تفضل Dr. Abdulaziz.
Okay. Thank you, Dr. Larry. Welcome all to this talk. Today, inshallah, I'm going to talk about embedded systems. My talk today, inshallah, is not going to be, we're not going to dig deep into the embedded systems. We are going to cover like the main aspects of the embedded system. So we are going to, I'm going to talk about what is the embedded system, some examples of the embedded systems, how embedded systems are actually different than the computer system that we are familiar with, what are the components of the embedded systems, and also I'm going to talk about studying the embedded system. If you intend to specialize in embedded system, what should you know and why you need to know this. And by the end, I'm going to talk about the job market. I'm going to talk about the job market in general, and then I'm going to talk about the job market of embedded system in Saudi Arabia. Okay, so this is like a brief outline of my talk today, inshallah. So what are embedded system? When we say embedded system, what we mean by embedded system? And in order to understand the concept of embedded system, we have to go back in history. When the computers was invented at the beginning, a single computer would occupy a whole room. It was something as big as this machine that you can see next to this man. As the time goes, technology evolved and computer systems also, the computers also evolved. And in the early 90s, we start seeing what we call the personal computers. It's a computer that you can have it in your home, and it's affordable for individuals. But this is not the end. The improvement and the evolutions continue. In fact, it's continue until we get to computers that are as big as our hands, or that can fit in your palm, and it also can connect to screens and keyboards and all these things. And nowadays, computer systems are not just the conventional computers that actually we are talking about, the ones that you connect to a keyboard and a screen. In fact, computer system now, it's a broader concept that can also have some computer on a chip. It's something similar to the one that you can see here at the bottom of the screen. It's a computer that is actually hidden, and it has some different features. So embedded systems are computer systems, but they have some, they are very small. They have some special characteristic. So let's talk about the formal definition of embedded systems. Embedded systems is actually a hidden computer system that has a special software developed to or designed to execute or perform some very specific function. And this computer system is either independent or it's part of a larger system that can communicate with other devices around us. So most of the time, we can see some embedded systems that are connected to the internet, and they can talk to other embedded systems also connected in the internet. We can classify, and one of the most difference between embedded system or embedded computers and the normal computers is that embedded system has a real-time computation. And we're going to talk about what we mean by real-time, inshallah, and next, inshallah. So embedded system can come in three different ways. We can have a stand-alone system, like the one that we can see here, like your smartwatch or your smartphone, or you can have something like the embedded system that controls your TV, your smart TV at home, or the computer system that controls the microwave. All of these are considered like computer system. They are hidden. They have some dedicated functionality that they perform. An embedded system can be part of a bigger system. So we can have a bigger computer, a bigger system that has many embedded system integrated into it. And we're going to see some examples of these subsystems or this type of embedded systems, inshallah. And maybe also we can have an embedded system that is connected to other embedded systems through a network. And this is actually going to take us to the IoT, which actually this type of embedded systems actually evolved into what we see nowadays as IoT. Type. The future is embedded, and embedded in is the future. I just quote some. I just bring this quote that I saw in one of the articles. It says that the information technology is on a verge of another revolution. So if you consider that what was happening in the past as like a revolution in the information and the information technology, embedded system is going to lead another revolution. Network system of embedded computers have the potential to change radically the way people interact with their environment. This is article published in 2001. And you can see that if you compare the world in 2001, like 20 years ago, and compare it to what we see today, it's the life that we are living is totally different. And our interaction with the technology, the involvement of the technology in our daily life has more impact than what was before. This revolution led by the embedded systems, which actually we are just at the beginning of this kind of revolution, and it's going to grow until to what we can see in what we can predict in the future, like Neum or the line in Neum, or these futuristic cities that we are going to see in the future. All of these like dreams, or let's say that this ambitious designs, those are all led by a good design of embedded systems, along with other technologies. Okay, so this revolution could well shadow the previous milestones in information revolution. This step, that the embedded system, the step that embedded systems are actually taking the revolution led by the embedded system can actually shadow whatever we have seen in the past. Okay, so let's see some examples of the embedded systems. What are examples of the embedded system, or the futuristic? How actually embedded system actually affecting our life nowadays, and how it actually is going to affect it in the future? The first example, and I think most of you have not seen this coming, is embedded systems are actually in today's car. In 1968, Volkswagen used a microcontroller or a microprocessor to control the fuel injection. This was the first computer used in automobile industry. And 30 years later, Volvo, in 1998, Volvo used around 30 embedded computer systems in their cars. And nowadays, the modern luxurious cars like BM or Mercedes, they use over hundreds of thousands of computer systems in embedded systems in their cars. They use these systems to control, for example, the fuel injection. They control the cruising system, the anti-brake, the anti-lock braking system, the airbags, all these modern technologies like the lane assisted, the parking assisted system. All of these are computer systems, and even some simple tasks are actually managed by computers in modern cars. So this is actually so when we talk about these kind of systems in cars, each one of these embedded system is part of the whole subsystem that controls the car. And in the future, we are going to see something like self-driving cars. Those are also going to be controlled by embedded systems. The embedded systems in the car are going to collect data from the sensors, data from around the surrounding of the car, and is going to process it and make some decisions based on that. Another example of embedded systems is in the transportation in the airplanes. So modern airplanes are actually generate massive. It's totally controlled by computers. And in fact, in Boeing 787, in one flight, the computer system, the embedded systems in the airplane generates over 500 billion bytes in one flight. And these data is not just about the surrounding of the state of the airplane. It also monitors the parts of the airplane, which one is actually wearing out, which one needs to be replaced soon, and also it has some those embedded systems actually going to help in the pilot to make better decisions to control the airplane when it has to, for example, the flap control system, the flight control, the monitoring the traffic, collision avoidance systems, all of these types of systems. These are computer systems that's going to help the pilot navigating through, help the pilot throughout his flight and get to the destination safely. Another very famous example is the smart homes. And when we talk about smart homes, people think of controlling devices by their mobile phones. They can turn on the TV, turn off the TV, and the lights, the AC. We're talking about a bigger or something more than that. We're talking about energy, energy controlling, reducing the energy, energy efficiency. Sorry, it's energy efficiency, reducing the consumption of the energy, provides safety and security, comfort. It also has to monitor, for example, the supply at the home. It can, for example, monitor the devices, which one is actually wearing out, which one needs to be replaced. All of these systems, it's like, it's not just going to control stuff. No, now with the AI and all these, the advancement in other technologies, along with the embedded systems, we can have, we can make our life much easier. We can have some better protective maintenance decisions based by using these computer systems. Like, why embedded systems are special? Now, we're all familiar with these computer systems, the laptops, the desktops. What makes those computer systems special? What is so special about these embedded systems? And we are going to talk about 5 of these different characteristics or special characteristics. The first one is they are not general purpose. They are special purpose systems. In other words, they are designed to perform some specific, sophisticated single job. Okay, so it has to do 1 or 2 tasks, and those tasks are very specific. So the design of the system, the design of the embedded system, the processor, the memory, all these things are actually integrated in a way that it helps executing this task efficiently and fast. Unlike the PCs, like the laptops or the general purpose systems, they can run any type of application. The embedded systems are designed for a specific task. The other characteristic of embedded system is they have some limited resources. So they are limited in power. So most of these embedded systems are battery powered. They run by battery. So you cannot. They have to manage their power efficiently. Imagine that you have your let's think of like a smartwatch. And if let's say that the smartwatch consumes a lot of power, imagine that you have to go and charge your. If I give you, let's say that if I design a smartwatch that is fantastic, it can do anything that you want, but you have to plug it to the charger every hour. So you have to plug it in the charge. You have to charge it every hour, and then you have to wait for half an hour, and then you can use it. So you are not going to buy it, because this is not a good design of an embedded system. Embedded system has to has a limited power. It has to work with this minimum power, the battery that comes from the battery. it has some minimum, a small memory where you can fit your data, you can fit your code, and everything has to fit in there. You have some, you cannot like have an embedded system that has a huge interface, like a serial port, because if the embedded system is very small, you cannot have you cannot use this conventional interfaces. And this will take us to the third characteristic. It has unconventional interface. Embedded system, when the embedded system when interact with the surrounding, it doesn't get the input through like a keyboard or a touch screen. Most of the time, those embedded systems get their input through some sensors, some weird ways, or some unconventional, let's say that, unconventional sources of information. And then when they generate some responses, they are not going to display something into the screen. They have to, for example, they have to move an arm, they have to open a valve or do some other task. So they need to interact with unconventional source of data, and they have to control unconventional what we call actuators or devices. The third characteristic is that they are reactive and they have some real-time operation. Well, what we mean by real-time, I'll just simplify it in using an example. So consider that the embedded system that actually controlled the seat belt. When la samah Allah, when the driver gets involved in an accident, then that system has to respond in less than 1 second. So the seat belt controller has to make a decision. It has to tighten the seat belt, and it has to open the airbag in less than 1 second. If it takes more than, let's say, that 2 seconds, by that time, maybe the driver is dead. So it has a constraint. It has to react to whatever happened, whatever the case, the accident, in a very short amount of time. It can, most of the time, this real-time operation requires a reaction or a response in less than 1 second. And the last one here, the last characteristic, it has some tight constraints. It has to be cheap so people can use it. No one is going to buy a smartwatch that costs like 20,000 riyals. No one is going to buy, for example, a car that costs like 5 million riyals. If it has, well, it's a super fantastic car. It can do everything by itself, but it costs like 5 or 10 million riyals because of all these embedded systems that actually in it. It also constrains in the size and weight. So, for example, if you are if we consider like an embedded system as a smartwatch as an embedded system, it has to fit in someone's hands. It cannot be bigger than that. It has to have like a decent weight. You cannot. No one is going to wear a watch that weighs like half kilograms. Right. So now let's talk about what are the components. When we talk about embedded systems, we say that they are different than the normal computer systems. What are the main components of an embedded system? The first main component is, since it's a computer, then we have to have a microprocessor. We are going to have a microcontroller that have a microprocessor, a memory, and also it has some interface. It has some pins. It has some kind of an interface that allows this microcontroller or microprocessor to interact with the environment. It has some analog sensors. It has some analog data coming into the microcontroller or the processor. And one of the main things here is we will need to have a converter that's going to convert the analog data into digital. When we talk about analog, it means something that has a continuous value, like the temperature here. So the temperature, it doesn't have like a discrete. It can be. It doesn't have discrete values. It cannot. In other words, it's not like the temperature is 35 or 36. It can be any value between 35 and 36 as a real number. So we have to digitize this value. We have to convert it from this number into something that the computer understands as digital. It has to deal with actuators, and some of these actuators can read or is controlled by like a digital output. Some of them are controlled by analog signals. So you have to have they have to have some kind of digital to analog converters, which actually is something like moving a robotic arm, opening a valve, moving running the motor for at some speed, increase the speed, reduce the speed, change the direction. All of these things are actually has to be controlled by the embedded system. And the last component of the embedded system is what we call an embedded software. So the embedded software is not like any other software. It has some special characteristic. The embedded software has to be concise, short. It has to know all these components, because you are going to design or write your code. This code is going to interact with these these inputs and outputs, and also with all the resources of the CPU. You don't have the embedded systems. Most of the time, they may not have like an operating system to control all these things. So you have to the software needs to deal with all these low level specifications. Okay, right. This is like a quick overview about the embedded systems. Now let's talk about what should I learn in order to be an embedded system engineer. Well, what you need, we're going to talk about 5 things that you need to learn, and the first one is microprocessor and microprocessor architecture and interface. You need to know, as an embedded system engineer, you need to know how your processor, the processor in the embedded system actually works, how it's built, and how it's actually connected, how it communicates with the input-output devices, the analog to digital converter, the digital to analog converter. And that's because when you write your embedded software, you have to calculate, you have to time your program. You have to make sure that your code is not going to take more than some amount of time, because you have a deadline that you have to meet. In the seatbelt example, for example, you have to react within a couple of seconds or less than 1 second. So you have to design your code such that it's going to react in this amount of time. So you need to know how fast is your processor going, how fast is your processor is going to execute these instructions, and how it's going to how long will it take until it reads the data from, let's say, that the sensors in the car, and how long will it take until it reacts to this accident. You will need also to know about the CPU communication interface. So there are some standards that manage the communication between the microcontroller and the sensors and actuators. And as an embedded system engineer, you have to know these communication and those protocols, because eventually when you get or you connect your system to a sensor or actuator, you have to communicate. You have to talk the language that this device actually understands. So you have to know the protocols. You have to know all these. You need to know the protocol. You need to know the way of the communication, the speed of this communication. Which one of those different protocols is more suited to your system? You need also to know about the analog to digital conversion and digital to analog conversion. You are going to read the data as analog and convert it to digital, and then you are going to generate your commands, the commands to the actuators as digital data. You have to know how to convert it to analog if that actuator actually requires some analog information. You need also another very important aspect that you need to know is what we call the real-time operating system. And when we talk about real-time operating system, we are talking about the different family of operating systems. It's not like the ones that we are familiar with. It's not like Windows, Linux, the Apple. It's totally different. Those operating system, the real-time operating system, they have some special interface. They have some special functionality that can help the embedded system meet the deadline. So they are designed in a different way. So if you want to write a program to run on these systems, you have to adhere with, you have to understand how they work. You have to understand how to communicate, how to utilize these real-time operating systems. And the last one is you need to know how to design an embedded software. Designing an embedded software is, as I mentioned, it's different than designing a software for a PC or for general purpose application, because the type of processors here is different. The interface, how you can communicate, there is no operating system, so you cannot just read from a keyboard. You have to read from, for example, the sensors, and then do the comparison, the conversion. Okay, right. Now let's go to the last part. Let's talk about the job market of embedded systems in Saudi Arabia. Well, the embedded system, the job market for embedded system engineers is, in fact, is actually evolving. Now we are at the beginning, or we are just seeing that the starting evolution in Saudi Arabia. It's not there yet, and one of the good things actually comes with Corona is this digital transformation. So people are going to rely on digitization in the future. So the market of the embedded systems engineer is still evolving. There are still jobs in the market, and there are still companies are coming into the Saudi market. Here is some of the fields where, as an embedded systems engineer, you can work in. So you can work in oil and gas, logistics company, security solution companies, military and defense. This is one of the biggest markets actually in here right now in Saudi Arabia. In IoT embedded systems is part of the IoT and digital transformation. Now we are talking about smart homes, smart plants, smart buildings, where this is also another field where an embedded system can work in. I just want to highlight something here. One of the studies actually it indicates as of March 2020, which means that a year from today, the average salary for an embedded systems engineer in the US is around $80,000 a year, which is around, if we convert it, if we estimate it in Saudi riyal, it's around 25,000 riyals per month. So it's around 24 to 25,000 riyals monthly. So this is the average salary in the US. And we are, and this wave is going to come here in Saudi Arabia, and there is a shortage in embedded systems engineering in Saudi Arabia, and those who are actually going to specialize in embedded systems, they're going to be the leaders in this field. Career opportunities as someone specialized in embedded systems. What kind of jobs that you can take? You can be an embedded hardware engineer. You can build the hardware of the embedded systems. You can be an embedded software engineer who writes or who develop firmware to these embedded systems. You can be a system software engineer who deals with high level, like real-time operating systems, kernels, and all other these things. You can be an embedded system test engineer who receive these embedded systems and test them for the company or where you work. You can be a systems engineer, embedded system architect, which is the one who designed the whole system. When you have an embedded system that has subsystems under it, so an embedded systems architect is going to design the bigger system and also is going to pass those smaller systems to the embedded hardware engineer. Okay, so this is going to conclude my talk. Intentionally, I tried to make it simple and make it short. I would like to thank you all, and let's open the floor for questions.
Thanks a lot, Dr. Abdulaziz. I was muted, so I was speaking to myself. Thanks for the interesting talk. I'm sure it will bring with it many questions. While let me see if anybody has questions, you could either type it in the chat or you could ask it. Just raise your hand. Now, I would like to start with some questions, if you allow me, while the questions are coming from the audience. Now, some people, say when you talk about embedded systems, you're talking about assembly language. I mean, some difficult programming to do. What has happened in the way we program embedded systems? Can you shed some light? Has it become easier? Are there easy ways to deal with that?
Well, thank you for that question, Dr. Lay. This is a good question. Programming embedded system, writing embedded softwares can be, you can write it at higher level. You can write it in C or or sometimes in even more advanced languages like Python, and you can actually write it in assembly. Writing applications in assembly, it's not just for embedded systems. Even for general purpose computers, you need to know some assembly if you are going to write some code that is actually closer to the hardware. So if, for example, if you are going to write the drivers, for example, or you are going to write some parts of the operating system, yes, you need to know assembly. But nowadays, writing programs or writing softwares for embedded systems, you can it's not necessary to be in assembly. You can write it in C, you can write it in C++. The compilers are going to convert this into assembly, and they're going to take care of this thing, this conversion.
Now, speaking about again, I mean, some of what people may think when you talk about embedded systems, to many people, they think of Arduino, as an example, and definitely it's one embedded system. But
right.
If somebody would like to go and learn about embedded systems, what should he expect? Like, how does the landscape look like? What are the different kinds? Are they all, for example, like Arduino, easy to use? Are there ones with different capabilities? And how do you categorize them from that standpoint?
Well, Arduino is yes, it's an embedded system. We can say that it's an embedded system, but it's an embedded system for hobbyists, for people who are trying to do something at home. It's not, no company no one adopt or use Arduino for a real product, or they use it for industrial grade embedded systems. When I think of Arduino, I think of like comparing Arduino to embedded systems in industry. I think of it like when you talk about building a real house, or building a house using a Lego. So building a house using a Lego is like building an embedded system using Arduino. So you can use Arduino to just build a model or build a prototype to test the concept, whether it's going to work or not. But you cannot build a system or a real working system using the Arduino. This is the first thing. The second thing, actually, when we talk about embedded system, we are not just talking about these microcontrollers. And we said, okay, this is the microcontroller, program it, connect it to these actuators and these sensors, and that's it. No, we're talking about something more. If you have, if you're going to design, for example, when we talk about the embedded systems in the car, so you have so many of these embedded systems. You have one for controlling, for example, the fuel injection. The other one is controlling, for example, the airbags, the seat belt, the cruise control, and you have to get those systems interact with each other, share information, process these information. This is a whole system. It's not just one microcontroller connected with some sensors and it controls some actuators and that's it. No, we're talking about a complete system of multiple such microcontrollers.
Okay, well, thanks. That's a very nice way to put it. Now, something that I feel I missed from your talk, well, maybe you can touch upon it here. There is a lot of talk now about what we call edge computing, meaning doing processing close to where the data is generated, and usually the data is generated at the embedded system. So what has happened in the embedded system world to accommodate this new shift? And by the way, does that have any role in the Saudi job market for embedded systems?
Yes, thank you. Actually, you talked about one of the missing point. I was going to talk about it and forgot it. Edge computing is, as you define it, processing the data where it was collected or where it was collected. And the driver for this kind of paradigm is the evolution or the advancement in the embedded systems or the processors and the embedded systems. At the beginning, when those embedded systems are actually introduced, like let's say that around 20 years ago or around that, the processor in those embedded systems were very, very simple. So they mainly barely can just gather the data, and they cannot do any kind of processing. They just gather the data, collect the data, and then they send it to a main server or some other device to do the processing. With the advancement in designing the processors in these embedded systems, now the processors become more capable of doing more processing. So embedded systems designers think why we don't process the data or do some pre-processing or half of the data before we send it, and then instead of like sending a whole bunch of data, we send whatever is needed to be shared with others. And if we need to make a decision, then we can make a decision at the edge, which makes that the decision is faster and the output can meet more tighter deadlines. So yes, embedded systems is actually a part of this like edge computing. I can think of it as like under the umbrella of the IoT, along with embedded systems, the edge computing, and the communication that is going to that's happened. In fact, I was talking to some people recently, and they talk about that people always fascinating about the big data. Big data is just collecting the data and then you do the processing in the cloud, for example, or in a centralized or a server where you collect all these data and then you do the processing. Now people think of what we call small data. The small data is the data that this edge device or this embedded system actually collect. So now they want to develop a way so that since those embedded systems are not, and they have some processing power, some good processing power, they can do some of the processing and they processing to this data and make some decisions and come up with some conclusions based on the amount of data that we have here.
Okay, well, thanks. Now, I would like to shift to our department. So, as you know, the CO department is rich when it comes to the embedded system expertise. So, if somebody is now, whether do you think that students who are not in the COE can they benefit from this? Like, for example, I was approached by a student probably a couple of years ago from chemical engineering, and he wanted to do a senior design project where he used embedded systems to do some process control of certain, uh, process, production. So what do you say to those people who are, interested, but maybe from a different discipline?
Well, I can think of embedded system as something that, as computer engineers, we provide to other disciplines. So let's say that student from chemical engineer or mechanical engineer, or someone who is like designing a something like a car. We're not expert in those systems, and in like designing a car or designing a plant for petrochemicals or something like that. But you can think of the embedded system like a service that can be provided to other discipline, to other people. So when we talk about, for example, the smart factory or smart plant or a smart building or smart, these are actually services as computer engineer we offer as, or embedded systems engineer. It's offered to others in other discipline. So yes, as an embedded systems engineer, you can do projects for other discipline, like mechanical, like chemical, like petroleum.
And can they take courses in? Do we have courses that are available for other students?
Well, and as of now, I don't think so, because well, in order to get to know about the embedded system, you have to know some background.
Yeah.
You need to know the computer architecture. You need to know the communication and real-time operating system, and all of these actually is not in one course. We cannot have it in just one course. We don't have it in one course. We have it in multiple courses. So the student has to go and has to take those courses in order to get to the embedded systems. It's not like it's just programming. If you want to just go and do the programming, you can do that. But you're not going to have an efficient embedded system. You're not going to be able to, for example, meet the deadlines, design your system to have these real-time operation. You may not be able to control these actuators or get the data correctly from the sensors.
Okay, well, but I think also, speaking of this, maybe we should highlight that we are going to offer a CX, a concentration in IoT, which includes one course on embedded systems, and also an MX program, which is also going to cover embedded systems, real-time systems. And since we have our chairman, Dr. Ayman, if you allow me, I would like to invite him to maybe talk about the two programs. Dr. Ayman?
Yeah, as you said, Dr. Lai, you are leading both programs. Inshallah, next semester we'll start the concentration on Internet of Things. And the first course actually in that concentration is called the Introduction to Smart Systems, which will cover the fundamental knowledge of embedded systems. So even for those students coming from other majors, they will be given the needed background. And then we have Internet of Things, Industrial IoT, and Data Analytics. Also, the master program, we are offering the Internet of Things and embedded systems. So this is interesting because it combines both areas. And as Dr. Lai mentioned, it will cover basically smart systems, real-time systems, all the courses for IoT, IoT security. So I think that will be embedded software engineering. So that will be a very interesting, actually, master program. Regarding cloud and edge computing, inshallah, this will be our next program that we are planning to focus on. So next year, we'll work, inshallah, on designing a concentration for the undergrad that focuses on cloud and edge computing.
And is there a plan to offer a concentration on embedded systems for undergrad, or is that something?
Actually, we considered this year, but we thought that we should start only with 2 concentrations, and then maybe next year, if we find good interest, we can also consider that. It was under consideration, but we delayed actually the proposal.
Okay, well, thank you, Dr. Ayman. I think we have a rich audience. If you allow me, I would like to also invite Dr. Yaqub. He was here. I don't know if he's still here. Maybe, yeah, he left. I wanted him to talk about the low power aspects of embedded system. And for electrical engineers, they still have relation to embedded systems. And one of the aspects is, as you mentioned, the low power. And with this comes a very interesting challenge, which is how do you generate power for embedded systems? And there are interesting ideas on even getting power from RF, like from radio, the signals that are floating in the air, which is, I think, there are all nice ideas connected to embedded systems as well. Now, we also happen to have Dr. Ahmed. Maybe Dr. Ahmed can shed some light on the security of embedded systems. He's leading the development of a course on security of embedded systems, and the security in embedded systems is different than normal systems. Maybe Dr. Ahmed can tell us why.
Yes. Assalamu alaikum.
Salam, hello, Dr.
Hello, حياك الله. Thanks for the question. Very interesting question. Well, I mean, security in general, the fundamentals of security applies to so many domains. But obviously, when you talk about the IoT and embedded systems, it has its own, specific, limitations and I would say concerns. Overall, the fundamentals of security of computer systems is probably the underlying security requirements is very similar. However, they are different when it comes to IoT. Obviously, the fact that IoT systems comes in different shapes and sizes, and so many platforms, many different kind of systems, embedded systems connected through the internet. This creates a huge attack surface, which is quite different from the very much standardized, typical computer networks found in the enterprise. So with that comes so many challenges. So the course we are working on will be part of this master program. We'll try to focus on this interesting domain. This IoT and embedded system domain, giving some background material on computer security in general, then, focusing on this specific domain, inshallah. So that's all I wanted to say.
Yeah, well, thank you for the answer. That's a very enriching one. So IoT is, again, it's the coming wave, and security is crucial. Now, Dr. Abdulaziz, I don't know, we have 5 minutes more. I would like to ask the crowd if there are more questions. Are there? You can chat, or you can open the mic and speak if you have questions, please. Okay, maybe can I challenge you with some questions, Dr. Abdulaziz, if you allow me?
Yes.
In your definition of embedded systems, you said it's usually it comes with a specific design, like it is for specific applications. Now, people, when they see Arduino, Raspberry Pi, some other devices, embedded systems, they kind of do everything, right? So how what makes those systems different? Are they still considered embedded systems or not?
Yes, these are embedded systems. And when I say that they are designed for a specific, to do a specific job, I mean, the whole system is actually going to, is designed to do a specific job, not the processor. So when you design, let's say that you have your Arduino, you configure it, you connect it to some sensors and actuators or some other devices to do some specific job. You cannot have the Arduino is not like your let's say that like your laptop. One day you can run, for example, Microsoft Office. Next day you can use it for web browsing. The other day you can use it for example, gaming or some other or presentation. Those devices, when the whole system, I'm not talking about the microprocessor itself, it's whole designed to do some specific job, and their processors, the processors is actually they have different way to communicate. Even if you want to connect it to other like sensors, they have some communication protocols that are actually those devices can use, so they can communicate with a specific type of sensors or actuators. So you cannot connect it to any other device. And it's not like with any other device. So that when I mention specific, I'm not talking about the processor, the task that the processor is capable of doing, but I'm talking about the system. The system is designed to do a specific job. It's not a general purpose. It's not something that you can change every day. So, for example, you have a system that is controlling, for example, the lights. So it's going to control the lights all day. It's not going to control the lights and then you can just unplug it and use it to control the AC. You have to redesign the system. Although you can use the same microprocessor, but you have to redesign the system. You have to come with a different interface. You have to come with a different software to.
And maybe because these systems can do a lot of things, that's what makes them unsuitable for many applications, right?
Yes.
Because they're also very generic. They cannot do what the specific system can do. So, okay. Well, I would like to thank you, Dr. Abdulaziz. I have other questions, but time is limited. So I just would like to open, and I was hoping for some questions from the crowd, but there isn't many, as I can see in the chat. So I would like to thank you again for the talk, for the entertaining questions and aspects. I would like also to thank those who attended with us. Inshallah, we are going to have more of these seminars. I think in 2 weeks we'll have our next seminar, inshallah, by Dr. Abdulaziz as well. Not Dr. Abdulaziz Tabakh. So inshallah, until that time, I would like to thank you all again for coming. Shukran, Dr. Sadiq is here. Shukran, Dr. Ayman and Dr. Ahmed and Dr. Yahya for the moderation. Dr. Mudawar is also here. I just saw the name.
Thank you,
everyone.
And a wonderful talk, Dr. Abdulaziz.
Thank you, Dr. Sadiq.
You two were fantastic, by the way.
Thank you. Okay, في أمان الله جميعا.
Okay, شكرا جميعا. I'm going to close the room now. السلام عليكم.
لا تقفل علينا الباب يا محمد.
لا I have to run to another meeting. يلا السلام عليكم.
يلا في أمان الله.
شكرا أبو عمر.
الله يعطيك العافية.
مع السلامة.